General Chemistry 1, Chapter 2, The Components of Matter. In this chapter, we'll discuss some concepts in chemistry, including elements, compounds, and mixtures, Dalton's atomic theory, the atomic theory today, the periodic table, bonding, formulas, names, and masses of compounds, mixtures. Element is the simplest type of substance with unique physical and chemical properties. An element consists of only one type of atom. It can't be broken down into any simpler substances by physical or chemical means. For example, silicon is an element. Helium is another element. In nature, many elements exist as separate atoms. For example, helium gas contains atoms of helium that are separated from each other. On the other hand, some elements exist as molecules. A molecule is a structure that consists of two or more atoms that are chemically bound together, and therefore they behave as independent units. For example, in oxygen gas, two oxygen atoms combined together forms a molecule O2 by a chemical bond. In molecules, the elements are present in fixed parts by mass. Okay, for example, oxygen molecule always O2. Okay, if it's 3 oxygen combined together, that's not an oxygen molecule. Okay, water contains 3 atoms combined together, so 2 hydrogen with an oxygen forms 2 chemical bonds. Okay, so this is H2O, which is a water molecule. Okay, the ratio hydrogen oxygen always 2 to 1. Okay, and this is water molecule. So in oxygen, the 2 atoms are the same element. In water, in water molecule, you have 2 different types of elements. One is oxygen, one is hydrogen, and this is called a compound. Compound is a substance composed of 2 or more elements that are chemically bonded. Water is an example of compound, where water molecules contains oxygen, hydrogen that are chemically bonded. Okay, another example is carbon monoxide. Okay, chemical bonds between one carbon and one oxygen, and this is a molecule. Okay, now if 2 elements are the same, such as oxygen, then that's not a compound. Even though it's a molecule, it's not a compound, it's an element, because the 2 atoms are the same element. Okay, here in compounds, you also have molecules, but they have different elements. Now, if these 2 different elements are not chemically bonded, then it's called a mixture. For example, you have hydrogen and oxygen. Okay, so hydrogen gas contains molecules with 2 hydrogen atoms bonded together, so it's a hydrogen molecule. And this one is an oxygen molecule. When you mix hydrogen molecule, oxygen molecule together, these 2 has no chemical bond, and therefore the whole thing is a mixture. A mixture is a group of 2 or more elements and or compounds that are physically mingled together. They don't have chemical bonds. If you dissolve table salt in water, table salt is a compound because you have sodium and chlorine with a chemical bonds between them. So this is a sodium chloride, sodium chloride, is a compound. Water is also a compound because two elements chemical bonds together, so it's a molecule, it's a compound. When these two mix together without chemical bonds, and this is a mixture. This table shows some properties of three elements: sodium, a solid, also a metal. It is silvery and shiny. Sodium is very reactive. It can react with water violently. Chlorine is a yellow-green gas. Chlorine is very poisonous. When sodium and chlorine combine together, they make a compound called sodium chloride. And sodium chloride is a white solid which has a very high boiling point and melting point compared to sodium and chlorine. It is amazing that two very reactive and poisonous substances rearrange their atoms and form a product that is completely different from their reactants, and it's edible. Sample problem 2.1. The following things represent an atomic scale view of three samples of matter. Describe each sample as an element, compound, or mixture. To answer this question, we need to examine the component particles. A sample that contains only one type of particle is either an element or a compound. The particles of an element consist of only one type of atom. The particles of a compound have two or more types of atoms bound together. Now this may sound be confusing to you, but let's look at a few examples. In hydrogen gas, in helium gas, we only have helium atoms. Okay, so helium atom is the particle that make up helium gas. In hydrogen gas, on the other hand, the particle is hydrogen molecule. Okay, each molecule has two hydrogen bonds together. So this is the particle make up the hydrogen gas. Another example is hydrogen chloride, which is an acid. So it is also made up of molecules, hydrogen chloride. So it has two atoms bound together. So this particle is a molecule. Okay, so the first particle to make up the sample is atom. The second and the third are both molecules. The first one is called element because it only consists only one type of atom. The second one is also called element. Even though it's a molecule, it's an element because it has only one type of atom. Okay, molecule has two atoms but the same type. Okay, so it's an element. The third one, on the other hand, is called a compound because the molecule has two types of atoms. Now, if we combine this together, so if we combine, let's say, helium and hydrogen, then we got a mixture because you have different particles, okay, component particles. So one is atom, the other is molecule. Or you can combine two molecules, hydrogen and hydrogen chloride. So if we combine these two together, that's a mixture. Okay, two different particles. Let's start with the simple ones. In B, we only see one type of particle. In fact, only one type of blue balls, and that represents atoms. So this is made of one type of atom. It's an element. In C, also one type of particle. or molecule. This molecule has two types of atoms bound together. If you look closely, you will see blue ball and gray ball inside. So two types of atom bound together to form molecule, and therefore this is a compound. So compound has one type of particle, and that's molecules. Okay, one molecule, but the molecule has different atoms. In A, however, you will see this is a molecule with two green balls, and this is another molecule, different type of molecule with red, yellow, red. Okay, so we have a mixture of different molecules, and therefore it is a mixture in A. You have seen that chemical reaction convert a substance to another substance. For example, the reactive sodium and poisonous gas chlorine add together give you edible table salt, sodium chloride. Here is another example. Lead nitrate solution. So this is a transparent solution. And sodium chromate solution, which is yellow. When you pour the sodium chromate solution into lead nitrate solution, and you will see yellow precipitate, and that is sodium lead chromate is a solid. Okay, so A react with B to form a compound C. Okay, now if you weigh them, you will find that the total weight before reaction, you add A plus B, the weight, equal to the weight of the product C. This is a odd type balance to weigh the sample. So from this observation, scientists draw a conclusion that is the total mass of substances does not change during a chemical reaction. Even though the reaction convert AB into C, make a different compound, the weight doesn't change. And this is called the law of mass conservation. Here is another example. When 56.8 grams of calcium oxide react with 44 grams of carbon dioxide, the product is calcium carbonate, and if you weigh it, it's 108 grams. Now if you add the two reactants together, you get exactly 100.08 grams, and that equal reactants, the sum of the reactants weight equal to the weight of the product. So the total mass substance present does not change during chemical reaction. In the last slide, calcium carbonate is synthesized by reacting calcium and carbon dioxide. If we perform a chemical analysis on 20 grams of calcium carbonate, you will find 8 grams of calcium element, 2.4 grams carbon, and 9.6 grams of oxygen. And that is, in the sample, 40% of the mass is calcium, 12% carbon, and 48% oxygen. And that is the composition of the calcium carbonate made by the chemical reaction. It turns out that calcium carbonate has different forms. It can appear as a marble or a coral. But if you do chemical analysis, they have the same composition: 40% of calcium, 12% of carbon, 48% of oxygen. This fact is expressed as a law of definite or constant composition, and that is, no matter what the source of a compound, in this case calcium carbonate, its elements occur in the same proportion by mass. Sample problem 2.2. Analysis of 84 84.2 gram of uranium-containing compound pitchblende shows it is composed of 71.4 grams of uranium, with oxygen as the only other element. So you have uranium and oxygen, and you know uranium, and therefore oxygen can be calculated by the difference. So the question is, how many grams of uranium can be obtained from a 102 kilogram of pitchblende? So here we have a small sample, okay, which is 84.2 gram uranium containing compound, and here we have a large sample, a small sample, a large sample. But as we already learned, the mass ratio should be the same, okay, no matter what source is, okay, they should have the same ratio, and therefore we can use the small sample to calculate the ratio and use that as a conversion factor to convert the mass to a kilogram total mass to the uranium mass. Okay, so here is our the plan. First, from 102 kilogram, the larger sample, we calculate how many kilogram uranium from using the ratio. Okay, use this ratio to calculate kilogram of uranium, and then because it asks for grams, and therefore convert kilogram to grams, okay, of uranium. Let's first think about the ratio as a conversion factor. The small sample, 84.2 gram pitchblende, contains 71.4 grams uranium. So we can write this as a ratio, as a conversion factor. So one way to do it is to use pitchblende mass as a denominator and the uranium as a numerator. The reason we do that, because now if you multiply by the mass of pitchblende of the larger sample, which is given 102 kilogram, then you can see mass of pitchblende, mass pitchblende cancel each other. What you get is the mass of uranium. So that gives you the mass of uranium. Now, because the given mass of the larger sample is in kilogram and the small sample in gram, so you need to have the same unit. Since in the small sample both are grams and grams, so you can think they have the same ratio, so you can add a kilogram. Okay, if both are gram, all right, so you just times 1000, both are the same. Okay, so 84.2 kilogram pitchblende also give you 71.4 kilogram uranium. So use that as a conversion factor. So here is the equation. We start with 102 kilogram pitchblende, which is from the larger sample, and from small sample we have this ratio, which is 84.2 kilogram pitchblende contains 71.4 kilogram uranium. And if you check the unit, so kilogram pitchblende, kilogram pitchblende, they cancel each other, and what you get is the kilogram of uranium. And then the numbers 102 times 71.4 divided by 84.2 give you the answer 86.5 kilogram. Okay, we start with kilogram, we end up with kilogram. Now the question asks you about grams of uranium. So last step, you use a conversion factor, 1 kilogram, 1000 gram. So kilogram cancel, give you the final answer, 8.65 times 10 to the 4th power gram uranium. Experimental observation also leads to another law called the law of multiple proportions. It says that if elements A and B react to form two different compounds, for a fixed amount of A, the different mass of B in the two compounds can be expressed as a ratio of a small whole number. For example, carbon and oxygen forms different oxides, and let's define them as A and B. So here is A, here is B. Assume we don't know the molecule, all right? And in A, the analysis show it contains 57.1% in mass of oxygen, 42.9% carbon. In B, it contains 72.7% of oxygen, 27.3% carbon. Here shows the grams of oxygen and the carbon in compound 1, A, and compound B. We can calculate the ratio of oxygen over carbon in compound A and B. Now notice that the ratio carbon over oxygen over carbon means every 1 gram of carbon, how many grams of oxygen. For example, here this means 1 gram of carbon, you have 1.33 grams of oxygen. And this means 1 gram of carbon, 2.66 grams of oxygen. In other words, we have a fixed amount of carbon. Both are 1 gram. Okay, in compound A, compound B, we have 1 gram of carbon, but in compound B, we have 2.6 grams of oxygen. In compound A, we have 1.33 grams of oxygen. So now we can calculate the ratio of these, the ratio oxygen over carbon from B to A. Okay, so 2.66 divided by 1.33, and that gives you 2/1. Okay, this tells you that if we fix the mass of one compound, in this case is carbon, then the mass of the other one, okay, in this case is oxygen, the ratio can be expressed as a ratio of whole numbers. In this case is 2/1. Through experiments, scientists discovered many laws and principles. In 1808, a major breakthrough came when Dalton postulated his atomic theory. The theory says that all matter consists of atoms. Atoms are tiny, indivisible particles of an element that can't be created nor destroyed. Atoms of one element can't be converted into atoms of another element. Now, this postulate is correct under most circumstances, but may not be right for nuclear reactions. Atoms of element are identical in mass and other properties, and are different from atoms of any other element. For example, hydrogen atom and another hydrogen atom, they are identical in mass and in size, everything, but it's different from oxygen atom. Compounds result from the chemical combination of a specific ratio of atoms of different elements. For example, water is H2O. The ratio is 2:1. So as long as it's water, the ratio is specific, 2:1, hydrogen and oxygen. Let's see how Dalton's theory explains mass conservation. In postulate 1, it says, atoms cannot be created nor destroyed. Therefore, chemical reaction cannot change the total mass. Postulate 2 says that an atom cannot be converted into other types of atoms. And again, it cannot change mass if atoms cannot change. And postulate 3 says that atoms of the same element are identical. Since every atom has a fixed mass, during chemical reaction, the same atoms are present but in different combination. Therefore, there is no mass change overall. Sample problem 2.3. The following scene represents an atomic scale view of chemical reaction. Which of the mass laws is illustrated? The mass conservation, the definite composition, or multiple proportions? To answer this question, we need to look at the numbers, the types, and the combination of atoms before and after reaction. If you compare the sample before and after reaction, you will find that we have 7 purple and 9 green atoms before reaction, and 7 purple, 9 green atoms after reaction. Even though after reaction, some atoms combine to form molecules, but the number of atoms, purple and green, do not change before and after reaction, and that illustrates the mass conservation. If we focus on the sample after reaction, you can see some molecules are formed, but all the molecules has the same composition. They all are made up of 2 green, 1 purple, 2 green, 1 purple. Okay, that illustrate, so the composition is constant, illustrating the law of definite composition. Since only one compound forms, so the law of multiple proportion does not pertain in this case. This diagram illustrates the experiment led to the discovery of electrons. A vacuum tube consists of a cathode and an anode. When the power is turned on, a ray could be seen coming out of cathode towards the end of the tube. Here are the observations and conclusions. Ray bends in magnetic field. So here is magnetic field, which indicates the ray consists of charged particles. Ray bends towards positive charged plate. So here is a positive charged plate. Okay, it bends like this. So that indicates that ray consists of negative particles. Ray is identical for any cathode. So these are the particles found in all metal. In 1897, the British physicist J. Thompson measured the ratio of the mass of the cathode ray particle or electron to its charge. In order to find the mass, we need to know the charge. In 1909, the American physicist Robert Millikan measured the charge of electron by oil droplet experiment. In this experiment, the apparatus contains a positive charge and a negative charged plates. A setup then that can generate oil droplet. The droplet can fall through hole in positive charged plate, and the oil droplet fall towards the negative charged plate. If the droplet is neutral, then the field between positive and negative charged plate has no effect on the speed of the falling of the oil droplet. When X-ray source is turned on, the X-ray knocks electrons from air molecule inside the apparatus, and the electrons stuck to the droplets. So now the droplet contains electrons. Since electrons has negative charge, and the falling speed now is affected by the electric field. By adjusting the field strength, Millikan made the droplet slow and hand suspended, which allow him to measure its total charge. By combining J.J. Thompson's mass charge ratio of electron and the Millikan's charge of electron, the mass of electron can be calculated. And the conclusion is 9.109 times 10 to the negative 28 gram. Electrons are negative charged, but atoms are neutral. What positive charge balance them? And if an electron has such a tiny mass as calculated in the last slide, what accounts for an atom's much larger mass? To address these issues, J.J. Thompson proposed his Plum-Pudding model, a spherical atom composed of diffuse positive charged matter with electrons embedded in it like raisins in plum pudding. In 1910, Ernest Rutherford tested Plum-Pudding model and obtained a very unexpected result. He used a positive dense alpha particle to strike a thin gold foil. The alpha particle can be detected by a screen on the back of the foil. The hypothesis is that if Plum-Pudding model is correct, the alpha particle should go right through the gold atoms. After all, he reasoned, an electron should not be able to deflect an alpha particle any more than a ping pong ball could deflect a baseball. The actual result is that although most of alpha particles go through the gold film, some of them actually undergo major deflection, indicating that some places inside the atom must be positive charged and high dense mass. Based on this experiment, Rutherford postulated that an atom is mostly space occupied by electrons. In the center is a tiny region which Rutherford called the nucleus that contains all the positive charge and essentially all the mass of the atom. He proposed that positive particles lay within the nucleus and called them protons. In modern atomic theory, the atom is an electrically neutral, spherical entity composed of a positive charged central nucleus surrounded by one or more negative charged electrons. The electrons move like electron cloud, and the nucleus consists of protons and neutrons. Protons has positive charge, neutrons has no charge. This table shows the properties of the three key subatomic particles. Proton has a positive charge, electron has a negative charge, neutron has zero charge. In SI unit, charge has a unit of coulomb, and so this is the value for the charge of one proton. This is for electron. They have the same value, but one positive, one negative. Here is the absolute mass of one proton, and this is for neutron, and you can see that very close to both 10 to the minus 24. The mass of electron, however, is about 1,000 times smaller. So the mass of an atom, is mainly focused, concentrated on the nucleus, proton and the neutron. The mass of electron contribute very little to the total mass of an atom. In this table, AMU means atomic mass unit. This is a relative number. It is the absolute mass times 1/12 of the mass of one carbon-12 atom. Now this unit is for convenience. So proton, neutron both have mass about 1 in atomic mass unit. Electrons, on the other hand, has a mass about 0.0005 in atomic mass unit. One atomic mass unit equals 1.66054 times 10 to the minus 24 gram. This table is commonly seen in periodic table. X represents the atomic symbol of an element. For example, hydrogen use H, helium use He. Now on the left side, Z represents atomic number. Atomic number is the number of protons in the nucleus. For example, in hydrogen, there's 1 proton in the nucleus, so we put 1 on the left side bottom. Okay, and A is called the mass number, which is the sum of the atomic number or proton number plus neutron number. Okay, then N is the number of neutrons. Now in atomic mass unit, 1 mass of proton and 1 mass of neutron are both 1. And therefore, when you add these two together, it's approximate the mass of the atom in atomic mass unit. For example, in carbon-12, there are 6 protons, 6 neutrons. So the symbol is carbon with 6 here represents protons or the atomic symbol number. Okay, atomic number means proton number, and 12 is the number, the sum of proton and the neutron. Similarly, in carbon-16 or oxygen-16, 8 proton, 8 neutron. So 8 represents the proton number or atomic number, and the sum of proton and the neutron is 16. Isotopes are atoms of an element with the same number of protons but different number of neutrons. Okay, same proton, different neutron are isotopes. For example, uranium has a proton number 92. Okay, 92, but neutron number can be 143 or 146. So when we write the symbol, we write U represents the uranium, the proton number 92, but the mass number is 235 for the first case. When you add the proton and the neutron added together, okay, it's the mass number. In the second case, U same, 92 is the same, but mass number 238. Okay, so note that isotopes are the same element, okay, because they have the same proton. As long as the atomic number or proton number is 92, that's uranium. Okay, if you change atomic number, then that's not uranium anymore. But even for uranium, okay, same proton number, the neutron number can change, and that gives you different isotopes. Sample problem 2.4. Silicon has 3 natural occurring isotopes, silicon 28, 29, 30. Determine the number of protons, neutrons, and electrons in each silicon isotope. Now we already learned the symbol, atomic symbol, atomic number, which is the proton number, and the mass number, which is the sum of proton and the neutron number. Now, in this question, A is given, X also given. Okay, we want to find others. Now, X is the atomic symbol. From periodic table, you can find this atomic symbol, which also give you the atomic number. Atomic number is the neutron number. All right, so therefore, with A and Z, then you can calculate the neutron number. Also remember, if atom is neutral, then the proton number equals electron number. So electrons can be found. So let's look at first one. So first, it's silicon. So from periodic table, you should be able to find atomic number for silicon is 14. and this can be found from periodic table. Okay, and then look at the first one. A is 28, so 28 minus 14 give you 14, and that's the neutron number. And the electron number is the same as proton number, which is 14. Okay, so you have 14 proton. Okay, 14 proton comes from this atomic number from periodic table. Electron is the same number because it's neutral, and the neutron number is A minus Z, and that gives you 14. For the next one, proton and the electron are the same. So proton, electron, the same. The neutron number is 29 minus 14, give you 15. The next one, again, same proton, same electron, but proton is 16 because 30 minus 14 give you 16. Sample problem 2.5. Silver, atomic number 47, has two naturally occurring isotopes, silver 107, silver 109. From the mass spectrometric data provided, calculate the atomic mass. So silver has two isotopes with different mass in atomic mass unit, and these are the abundance. Means that in nature, if you have a silver sample, it's a mixture of these two isotopes. 51.84% is silver 107, 48.16% is 109, silver 109. So what is the atomic mass of silver? So in periodic table, for example, we are not reporting atomic mass for 107 or 109. Instead, we are reporting the atomic mass for the average of these two, the mixture, okay, the atomic mass of the mixture of naturally occurring silver sample. So to calculate the average, okay, the atomic mass, to find weighted average of isotope mass, we use the individual mass, the isotope mass, multiplied by the abundance, okay, this abundance, and the mass times abundance, and then add together. So first you calculate the multiplication between the mass, individual mass, and the abundance, and then you add together. So here is the solution. For 107, all right, you use this mass times abundance, okay, and then for 109 you do the same, all right, and then add together, give you the weighted average of the isotope masses, and this is called the atomic mass of silver. This diagram briefly shows how mass spectrometer works. The key of the instrument is the magnetic field. A sample enters chamber and is vaporized and heated. An electron source provides electron beam that can knock the electrons out of the sample. So the atoms now are ionized because they lose electron. The ionized ions, okay, the charged ions, enter the electrical field and accelerate. It can be accelerated. When they pass magnetic field, they are banded and separated by their mass charge ratio, and then reach the detector. From the position of the detector, we can find the mass charge ratio of the ions. For example, if we see at mass charge ratio 20, there is a peak. Okay, that means a ion with mass charge ratio 20 reaches the detector. So in the sample, we have an ion with mass charge ratio 20. Now, if the charge of the ion is 1, then this gives you the mass. Okay, so the ion has a mass 20. Here shows a typical modern periodic table. In this table, each element has a box, and the box contains atomic symbol, atomic number, atomic mass. And this box is similar to the one we already introduced, but not exactly same. So we also have atomic symbol. We have Z represents atomic number, okay? And instead of mass number, here tells you the atomic mass in this periodic table. The periodic table is arranged according to the atomic number or the proton number of the element. For example, it starts with hydrogen because hydrogen has 1 proton, and therefore atomic number is 1. And then helium, 2 protons, atomic number is 2. And then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So neon has 10 protons. Atomic number is 10. The periodic table has columns, which we call groups. And there are 8 called main group elements labeled by capital A. So this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. These are all main group elements. In between, we have transition metal, transition elements, okay, labeled by B. So 3B, 4B, 5B. So 1B is here, 2B is here. Okay, we have inner transition elements. Okay, these fill the gap here. Okay, and we can see that the periodic table has different colors, and the color tells you whether they are metals, nonmetals, and transition metal or metalloids. Here is the instruction, and you can see according to these instructions, these are metals, metals, metals. Okay, metals are usually solid, shiny, conduct electricity. Now, the yellow color means they are nonmetals. Okay, nonmetals are usually solid or gas phase or liquid, and they don't conduct electricity. In between, here, the green one, okay, these are metalloid or semi-metals. They have property between metals and non-metals. Now, it is very important to realize that the elements in the same group should have similar property. For example, main group elements A. And so we know helium is a gas which is inert, doesn't react, is not very reactive. So neon should be similar. Argon, also gas, not reactive. So in the same group, they have same property. Fluorine, very reactive. Chlorine, very reactive. Poisonous gas. Okay, and lithium is a metal. Okay, reactive metal, react with water. Sodium also react with water, very reactive. Okay, potassium is a metal, react with water. So all most elements in the same group should have similar chemical properties. Also, some of the groups has common names that you need to know. For example, the main group elements 1A, okay, this group A is also called alkali metals. Okay, it not include hydrogen. Okay, they are called alkali metals. Group 2, okay, has a name called alkali earth metals. Okay, fluorine, chlorine, okay, this group, all right, is called halogens. And the last one, okay, group 8 is called noble gases. In addition to groups or the columns, the periodic table also contains rows called period. Period 1, 2, 3 until 7. So hydrogen is at group 1 and period 1. Beryllium, period 2, group 3. Argon, period 3, group 8. This shows some examples of metals, metalloids, and nonmetals. Metals are solid, shiny, conduct electricity. Nonmetals can be different color, solid, gas phase, liquid phase. Some of them are also shiny, solid, but they don't conduct electricity. Metalloid, many of them looks like metals, but they don't conduct electricity as well as metals. Sample problem 2.6. For each of following Z values, give the name, symbol, group, and the period numbers of the element and classify it as a main group metal, transition metal, in the transition metal, non-metal, or metalloid. Okay, so to find this information, we need a periodic table. So here it is. And for A, Z is 38. Z is the atomic number. In periodic table, you find the 38 here. Okay, and SR means strontium. So strontium, SR. Okay, and is group 2A and period 5. So it is group 2A period 5, and because it's 2A, so it's the main group element. Okay, and it is a metal. Okay, according to the color, it's a metal. Now, if you have a problem to find the name, okay, you already find SR. To find name on the cover of the textbook, there's a list of chemicals, alphabetical order, and so you can find strontium there. For B and C, we also need the periodic table, and for B, Z is 17, so periodic table find 17 atomic number, and that's Cl means chlorine, and it's group 7A, period 3, and yellow color, so it's a non-metal. Okay, next one, 27. So 27 is here. CO means cobalt, and group 8B, and period 4 is a transition metal. Although atoms are neutral, they may lose or gain electrons and becomes charged atoms called ions. For example, chlorine gas is made of chlorine molecules. Each molecule has 2 atoms. Inside the chlorine atom, there are 17 protons and 17 electrons outside nucleus. And because proton is positive, electron is negative, and you have same number of proton and electron, so they cancel each other. So the chlorine atom is neutral. There's no charge. Similarly, sodium metal is made of sodium atoms. Each atom has 11 protons and 11 electrons. Again, proton positive, electron negative, and you have same number of proton and electron. So sodium is neutral. Now sodium is a metal, tend to lose electron, and chlorine is a non-metal, tend to gain electron. When sodium and the chlorine are put together, sodium tend to lose an electron to give to chlorine. By losing electron, sodium now becomes 10 electrons. So still 11 protons in the nucleus, but only 10 electrons, because 1 electron gives to the chlorine, and therefore now the sodium atom now has more proton than electron. And because proton is positive, electron is negative, so sodium has an extra positive charge called sodium cation. On the other hand, chlorine atom, by gaining one electron, so the electron now becomes 18. And therefore, chlorine atom has one more negative charged electron than the number of protons, and the chlorine becomes negative charged, called chloride anion. Okay, so now we have a compound. One is a sodium cation, one is chlorine anion. One has a positive charge, one has a negative charge. They bound together by charge attraction force, or ionic bond, and this compound is called ionic compound. Sodium chloride is a white solid. As you saw in sodium chloride ionic compound, the ionic bonding is due to the attraction force between the positive charged ion, negative charged ion. There are several factors that influence the strength of the ionic bonding. First, of course, is the number of charge. The more charge the ions have, the stronger they attract each other. Okay, so first is charge. Okay, second is the size. The smaller the size of the ions, the closer they can be, and the stronger they attract each other. So the stronger ionic bond is between smaller ions with larger charge. Okay, and the weak ionic bonds is between the larger sized ions with smaller charge. In periodic table, we mentioned the main group elements, especially group 8 called noble gas. These elements are among the most stable elements in periodic table. In other words, they rarely react. Other elements, however, they tend to either lose electron or gain electron until they becomes the same structure as the noble gas elements. For example, let's look at neon. Neon has 10 electrons and 10 protons. Fluorine has 9 electrons. In order to get a structure same as neon, it needs to gain 1 electron. Okay, because fluorine has 9. All right, to get neon 10, it needs 1 more electron, and therefore fluorine tends to gain an electron. When fluorine gains electron, it becomes a negative charge anion, so F negative, because fluorine has 9 protons. To gain 1 electron, it becomes noble gas structure, 10 electron, but it has more electron than proton, so it's negative charge. Similarly, oxygen has 8 electrons. In order to get 10 as neon, it needs 2 electrons, and therefore it becomes a 2 negative charged anion. So it becomes ion with 2 negative charge. And what about nitrogen? Well, 7 to become 10, it needs 3. So nitrogen group 5, you need 3 negative. Now, this is not just for fluorine, oxygen, nitrogen. It's same for the elements in the same group. For example, chlorine. Chlorine has 17. In order to become 18 as argon, it needs 1 more electron, and therefore chlorine needs 1 more electron, becomes chlorine cation anion, 1 negative charge. Similarly, sulfur has 16. In order to become 18 as argon, it needs 2 electrons, so sulfur is 2 negative when it gains 2 electrons. Okay, these are non-metals. What about the metals? Let's look at the sodium. Sodium has 11 electrons. The noble gas element that closest to sodium is neon. Neon has 10. Sodium has 11. So in order to have the same structure as neon, it needs to lose electron. Okay, note that non-metals gain electron. Metals such as sodium lose electron because it has one more extra electron than neon, and therefore by losing an electron it becomes sodium plus, okay, cation, and it has a 10 electron structure as neon, so becomes more stable. Similarly, what about potassium? Potassium has 19 electrons, and the closest noble gas element is argon, which has 18. So from 19 to 18, again, it needs to lose an electron. When it loses electron, it has more positive charge, and therefore potassium is positive 1. Okay, and this periodic table we can look another way. So here is the noble gas. All right, the non-metals are on the left side. So this is group 8, and this is group 7. So to the left side are non-metals. They tend to gain electron. So the closer to the noble gas, the less charge. So fluorine becomes 1 negative charge, oxygen becomes 2 negative charge. It needs 2 electrons, and nitrogen needs 3 electrons, so 3 negative charge. On the other hand, on the right side is the sodium. Okay, so even though in this periodic table looks like sodium is far away from neon, but only 1 electron away from neon. Neon has 10 electrons, sodium has 11. So we can put sodium to the right side of neon, and it needs to lose an electron, so it becomes sodium plus. And the magnesium, on the other hand, has 12 electrons. It needs to lose 2 electrons, becomes magnesium 2 plus. Okay, so group 1 tend to lose 1 electron, becomes 1 plus, and group 2 needs to lose 2 electrons to becomes 2 plus, and it becomes same electron number of electron as a noble gas element. Sample problem 2.7. Predict the monatomic ion formed by each of following elements. To answer this question, we need to have a periodic table. So here is a periodic table, and for A, iodine, zinc, Z is 53, the atomic number 53. So in periodic table we can locate Z53 is right here, and we can see zinc, iodine is group 7, and as we learned, group 7 is a nonmetal that can gain 1 electron to form same electron as group 8. Okay, group 7 plus 1 electron to form 8 electron. Just like here, iodine to xenon 53 to 54, you need 1 electron. So it's gain electron, just like fluorine, chlorine to gain 1 electron to form neon, argon. So they are all 1 negative charge. So the prediction is you should get a iodide with 1 negative charge. That's true for all group 7 to gain electron to form noble gas structure. For B, the element is calcium and atomic number 20. In periodic table, you can easily locate calcium Z equals 20 in group 2. Okay, as we mentioned before, group 1 lose 1 electron. Okay, group 1 metal lose 1 electron. Group 2 lose 2 electron. So calcium will lose 2 electron to form calcium 2 plus. Okay, in fact, you will see that calcium has electron 20 and argon 18. So to achieve the noble gas structure, you need to lose 2 electrons. When you lose 2 electrons, you become 2 plus. Okay, and so that's calcium as B. Let's look at the C. C is aluminum, Z equals 13. So in periodic table, we find 13 right here. Okay, so it's group 3. Now group 3 should lose 3 electrons. Okay, if you look at the closest noble gas is neon. So neon is 10, aluminum is 13. So you lose 3 electrons, and therefore we predict aluminum to be 3 plus. Okay, the ion is 3 plus. Now some people may ask, can aluminum also gain 4 electrons to form argon? Okay, to gain electron to form argon, you need 1, 2, 3, 4, 5 electrons. So one is gain 5 electrons, one is lose 3 electrons. So it's easier to lose 3 electrons to form neon instead of form argon. And therefore, you can think about group 4 as a boundary. Okay, on the right side of group 4, they are nonmetals, they gain electrons. So nitrogen, for example, gain 3 electrons, oxygen gain electron, 2 electrons, fluorine gain 1 electron to form neon. On the other hand, on the left side, boron will lose 3 electrons to form helium, and the beryllium loses 2 electrons, and the lithium loses 1 electron to form helium. Please read your textbook, Chapter 2, up to the sample problem 2.7. Practice with the follow-up problems and get ready with the online homework assignment.